And greetings, friends. We are back on Wednesday today. So for class number 2, and let's go ahead and get started. We'll finish off interference today, and we will go to diffraction, and that will conclude what is necessary for the homework set number 5. So that'll be due tomorrow. Quiz tomorrow. Okay, not sure what happened there. It looked like I just kind of froze up for a bit there. Quiz tomorrow, and just by way of reminder, PLC 9 for today. No, not today, for Friday. PLC 9, that's Friday. Homework 5, Thursday. That's tomorrow. And we're going to do plus quiz number whatever. So we'll finish up interference today. We will get diffraction started, and we'll roll through some diffraction. We're looking at the second celebration in about a week and a half. I'm guessing it's about a week from next Tuesday. So Tuesday would be the 16th. So I think it's a week from then, maybe the 23rd or so. All righty. So we left off last time talking about thin films and thin film interference. So thin films is a great example of all of the types of interference put together. And so we need to deal with all of them. I'm going to do one more example today involving some thin films, and this is based off something called Newton's rings, which is a really interesting phenomenon, especially when considering that you can actually make a thin film out of air. Okay, so let's just describe Newton's rings for you really quickly. Under the heading of thin film interference. And so, suppose that you have two pieces of glass, right? So you might have a piece of glass that's kind of shaped something like this. And that might be resting on top of a piece of glass that's shaped like this. Okay, so if these are both glass, then this is an air gap in between the two pieces of glass. And now if I shine light with normal incidence, remember this is how we deal with thin film interference, consider normal incident light, then you're going to get an interference pattern here, right? Because you're going to get light transmitted. Yes, it'll bounce off the first surface, but we don't worry about that. We're going to get light transmitted off or reflected off the second surface here, bouncing out and then bouncing off here. We'll get those two will cause those two reflections will cause basically a thin film interference effect in the air gap. And one of your homework problems is dealing with this. You have a shape. It's a bowl shape, and I'm interested in the radius of the rings. So what I like to do is do an example on, instead of doing it this way, I'm going to actually do the photonegative of this. Let's have a wedge-shaped piece of glass, like this piece of glass right here, as if it was shaped like the air gap. And let's look at thin film interference from that. All right, so you can consider it to be kind of just the same shape as the air gap here. And so again, normal incidence, right? So light would be coming in directly onto the top surface at a 90-degree angle, or 0-degree angle, really, because we always measure straight off the normal. So light comes in here. Okay. And as we're observing this, right, so just like we would be observing from the top here to examine the interference between these two rays that bounced off the air, off either side of the air gap, we're going to do the same thing here. We're assuming incident light is straight downwards, and it's going to cause a reflection back upwards. So we're observing from the top, right, as if we're shining the light and we're looking straight down from the top. Excuse me, I apologize for my voice today. I seem to have been in the overuse category. So I want to look at the interference between light beams that reflect off the top and then reflect off the second surface of the glass here. Okay. Now, let's suppose that the person observing from above sees a grand total of 10 bright fringes, right? One on either end, and then 9 dark fringes in between. So let's assume that we have a bright fringe. Let's do this. Well, no, let's do this. All right, so this will be constructive interference. That'll be constructive interference. Okay, so we'll see bright fringes. Due to reflection here, and then there's in between. So I'm gonna have 1, 2, 3, 4, 5, 6, 7, 8, 9. Darn, 9. 10 total. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I did get 10 total. Okay. So we've got 10 total bright fringes. What we can do is assess what the light is doing at the top and bottom surfaces of the glass. Okay. So let me draw these pieces again here, a little bit up close. So if I take just this end here, and we'll call the thickness, let's call this thickness, for example, T1, and this thickness is T2, okay? All right, so let's suppose that this is a close-up of T1, okay? Now, I'm going to look at the light that's coming in from the top. It's going to bounce off the surface, and so we know that that's going to incur a phase shift, okay? So I'm not going to draw the incoming light, right? We already know it's there. I'm going to draw the bounce-off light. So it's going to be going, there's the bouncing off light. Okay, I'll draw the incoming light, fine. Like that. Okay? Remember, I don't draw normal incidence because it's directly straight back up along the same line. We always do it at an angle just to show the properties of the reflection. Nonetheless, it is coming in straight. Now, this first one, what will be happening to the phase of this first one? We're going from air into glass now, okay? This glass has an index. Suppose 1.5, that's usual for glass. So this ray here is going to be shifted by pi. It's going to be a half wavelength shifted. Okay. I look at the next ray. The one that's transmitted in, hits the second surface, and then bounces off. when it hit the second surface, what was it going to do? Notice it was going from glass into air, and therefore, when it's going glass into air, in other words, the light is going to be speeding up. Macroscopically, in the sense that it was going slightly slower in the glass. And now it's going into air, so it's going faster. We get zero phase shift. Okay. So I marked that with a +0. Now, if we look at what this means, now, in yesterday's video, we had the situation of light reflecting off successively increasing index materials, right? So they were always pi shifted, right? As soon as you're going up in index, you're going up on up on phase. So, in this case, we're dealing with waves that are, in general, already set up to destroy each other. This is how I consider it. I look at these waves and I say they're coming out already half a wavelength different. So their tendency just from this part is that they are trying to, right, they're trying to destroy each other. They're doing this, right? However, I'm noticing that I have a bright fringe here. So what has to be happening? Remember, we have those two other things in terms of interference effects to consider here. I have to consider the path length difference of the second ray as well as the wavelength reduction inside the glass. Now, what will be the condition of those such that I get interference that is constructive from these two waves? I need to shift them back. See, they're a half wavelength out right now. So I need to shift them back into phase. That means that the thickness here has to be some multiple of a half wavelength. All right. So I'm going to write down my interference conditions such that the path length difference is a integer multiple of half wavelengths inside the material. Those are the two conditions, right? I got a path length difference, and I got a wavelength reduction. So in this case, because they're already tending to try and destroy each other, I need to shift it back by a half wavelength. Therefore, the thickness of the material must be an integer number of half wavelengths of the wavelength material in the material. So I can write this as being my path length difference 2T1 equal to, right, because it goes in and then it goes out, so that's my path length difference is twice that thickness. And that has to be an integer multiple of half wavelength inside the material. So this has to be, since this is T1, I'll call this M1 plus a half times lambda. We'll just call it lambda naught divided by n. All right, so that incident light, maybe I'll go ahead and rename that. That incident light has some incident wavelength to it, which we can call lambda naught. Okay. So it's this stuff that's coming in, lambda naught. And when it gets into the glass, it's lambda naught divided by n. And it's some number plus a half, right? So this is going to be the thing that takes care of this phase shift. So this has a half wavelength phase shift. This is bringing in a half wavelength shift. And therefore, I am hoping to get them doing this when they're exiting, okay? They're exiting like this. Likewise, I can write the same thing for over here. Okay? I can write the same thing for over here. I can make the same arguments. And I could write that likewise 2T2 is going to be M. In this case, it's 10 bright fringes. So I started with an M1. I mean, I don't know what M1 is. Okay? I don't know if it's 1 or 2 or 3. What it doesn't. I just know that I've got to have the half in there in order to get the wavelength to shift back. But what I do know is if this is M1, then this is M1 plus 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9. So I got M1 plus 9 to give me 10 total bright fringes here. So I'm going to have M1 plus 9. Now I got a bright fringe again on the opposite side over here, so I'm still going to have to put the half in. And it's still lambda naught divided by n because it's the same material. Okay. Now I could find now the difference in sizes between the thicknesses. Okay. I can find how thick is the material. I can't find how thick is the material. I can find out how much thickness changes as you go from T1 to T2. All right. So I can say, all right, let's suppose that I'm going to find T2 minus T1. That's going to be the change in the thickness of the material. And I could do exactly the same thing here if I was thinking about the air gap in the glass situation. All right, so that's a delta in the thickness. If I subtract these two things, you're going to notice that the M1 is going to drop away anyways. The half is also going to drop away. And I'm going to end up with, I'm going to have to put the 2 underneath here. So I'm going to end up with 9 lambda naught divided by 2n. In this case, in which I had 10 total bright fringes. So it's a kind of nice situation in the sense that if I have bright fringes on either end, or I can look at a set of bright fringes, right? I'll have many bright fringes through here, but if I just look at the set of 1, 2, 3, 4, 5 or something like that, I could always do that minus 1 times lambda naught over 2n. And if I have a situation that is truly coming out with a phase difference in the reflected waves, then I should be able to use this as a way to find that thickness of a piece of wedge, or a wedge shaped, I should say. Okay. Now, if we knew what the incoming light was and we knew the index of glass, we'd be able to put numbers in, find that. But we'll leave that for now. This is good enough because we can make up numbers, but that's not really the point here. All right. Now, thinking about the problem on the homework, that's slightly different than this one, okay? Oh, that's hot. That's slightly different than this one, okay? In that case, I've got a bowl shape, okay? But you're going to use basically the same reasoning as I've done here, but you just have to deal with the bowl shape, okay? Now, I drew a triangle in there to kind of help you think about how to get the thickness at particular points based on what the radius of the bowl is, and then what the radius out to the ring is. All right. So think about how to get that. That's just a bit of geometry, but the process to solve that is basically the same as what I've just done here. Okay. Now you've got the extra step of dealing with the bowl shape, but it doesn't have to be super complicated. Use the triangles. Okay. That's what we're doing here. This is a great example for thin film interference, and what we are going to end up with here is just a quick reminder that thin film interference involves all 3 types of interference. Okay, so let's finish this off here with a bit of summary on wave interference. Okay. Okay, we've talked about the three types of ways to cause wave interference. Now, they can be caused by wavelengths being changed by going through materials. Okay, if a wavelength outside in air here goes into glass, it gets reduced by the index of the glass, and then when it pops back out, the wavelength increases again and off it goes. We've talked about the path length difference. Okay, the path length difference can be fairly ubiquitous. I mean, in the sense that we can use it in the double slit experiment, we can use it in the thin film experiment. There are different ways to come up with a path length difference. But the idea is that you draw it out and you see, oh, this wave traveled this much further than that wave. And therefore, there's a shift. Okay. So the path length difference in the double slit comes out to be d sine theta. Where d is the spacing between the slits and theta is the angle at which the interference is happening that you're interested in. And the last one here that we talked about in the context of thin film interference is reflection phase shifts. And the rule here is, actually we'll do it this way. If you are going from a material in which the index is lower and you're bouncing off a material in which the index is higher, in other words, there's an increase in the index, then there's going to be half a wavelength shift. Okay, so it's like index goes up, phase goes up. Okay, decrease means nothing. Right? It's not decrease means down, decrease means zero. Okay, so that's a zero. Now, double slit experiment, we concentrated mainly on number 2. Okay, thin films, of course, as I've been saying, we've got all 3. I will encourage, again, when solving, first of all, 2-slit problems, make sure you understand how to get the path length difference, and you understand how many wavelengths you can fit into the path length difference, or how many half wavelengths can you fit into the path length difference. That tells you everything you need to know about what interference is happening at different places on the screen, okay? And then if you use the small angle approximation, you can find out what those places are. All right? In the thin film situation, we talked about starting with this one. And I encourage that mostly because that's the way I do it. So if you have a better way of doing it, great. Go do it a better way, and then tell me what it is so I can make, so I can expand my worldview. All right. I always start with the reflection phase shifts because that helps me write down what's going to have to be true with these 2 types in order that the interference I'm looking for is happening, as I just showed you in that previous example. Okay. We did talk about intensity in the double slit experiment. And I can go back and revisit that a little bit. Double slit intensity. Now this is, I should be a little more careful with this. It's really the fringe intensity. Okay. for the double slit fringe intensity. And we were doing a little bit of this at the end of last time, where I was telling you that the intensity at some point on the screen is proportional to the electric field magnitude, amplitude squared. And then it came out to be 4 I naught, where I naught is an incidence through one of the slits, times the cosine squared of the angle between them. I think it's actually the half angle. Let me make sure I got this. Right here. It's the half angle between them. Yes. Okay. So that this is the intensity. Say through one slit. Okay. And this is the phase angle between the two electric field vectors. All right. So that if I have them lined up like this, then that angle is 0, and you get a maximum in the intensity. If I have them anti-lined up, then this angle is 180 degrees, but 180 divided by 2 is 90, cos of 90 is 0, and we're getting a dark spot, which is what we wanted. Okay. Because of that, we can actually go a little bit further into what this phase angle actually is. We can rewrite the phase angle as being, if I consider, well, let's do this. Let's do this. If I want to maximize the cosine squared, then I'm going to get a 1 from this, which is as big as it can get, right? When this is equal to some integer times pi. Sorry, integer times 2 pi. I can maximize this with 2. Actually, do I want to do that? No, I got it right the first time. No, I didn't. I had pi if it was m pi. Oh, now I'm confused. So hold on a second. 2m pi. If this is a pi, yeah, no, that's right. It's maximum. I was right. Okay. 2m pi is going to happen later. So this has to be a maximum. It's squared. That's what confused me. I forgot it's squared. So this is going to be a maximum when the argument is a multiple of pi. And it doesn't matter whether it's minus or plus because it's squared. All right, so when I look at what phi is then, phi is 2m pi, where this m, we know we have a way to talk about what that integer is based on where we're looking in the interference pattern, right? So if we look back to the interference pattern, where we said that d sine theta is equal to m lambda. Okay, now if I'm looking for construction, this m is the same as this one, because I'm trying to maximize the cosine here, and that's exactly what this m is doing. So if I just think about m as being d sine theta over lambda, that can go straight in here. Right? And therefore my phase angle in here looks like 2d 2 pi times is a way to think about the maximum, the angles to the maximum. So this will give you the relative phase angles between maxima in the double slit experiment. Good times. Alrighty, so there's this stuff. This is essentially the wave interference pattern. We've described where the bright and dark fringes are and why. We've described what intensities they are, and then we've used thin film interference to describe what we're expecting to see when light's reflecting off a thin film. Okay, great. So that's going to pretty much finish up interference. And what we're going to do now is look at what is happening when light's going through a single slit. So you think, well, if light's going through a single slit, we just did the double slit. Isn't it going to be way easier? No. It's actually a little more complicated. So, man, that's hot. So, we are not going to be able to do things quite as thoroughly as we did with the double slit, because it turns out that the mathematics is a little bit more complicated. It's not like it's a really big deal. It's just it's more time consuming, and we don't have that time. So what we're going to begin here is diffraction, and single slit diffraction at that. Now, you might ask, diffraction, what's diffraction? Well, let's take a look. I'll draw you the single slit setup first, and we'll take a look at that. Okay, it's the same basic setup as the two slit. Just got the single slit over here. Okay, light as usual, incident from the left, propagating left to right. So, right, we've got some incoming lambda here. Well, I don't call it lambda, no, let's just call it lambda. It's going to reach here, and then what's going to happen is the narrower the slit is, the more spreading out we're going to get. Okay? And this was one of the really confusing aspects of the ray model. The ray model breaks down because what we would expect to see if we shined light through this slit would be a shadow, and only a small bit of light is making it through, and this would be the size of the slit as projected on the screen over here. But unfortunately, that's not what happens. What happens is we get, again, a pattern of light and dark fringes, just like we did with the interference, okay? So when the light comes through here and the slit is narrow enough, what happens is light spreads out, okay? And it spreads out just as if you were thinking of dropping a rock into a pond, right? You drop a rock into a pond, and then you watch those ripples spreading out like that. That's basically what happens to the light as it goes through this slit. The idea that it does that, and therefore propagates in pretty much every direction, is a conceptual model, which is pretty useful. And I will say this, it's useful to think about. Not so useful, at least in my opinion, to draw it. But I'll draw it here just to give you the idea of what the model looks like. But I'm never going to draw it this way for like purposes of showing something. So suppose that these are the crests. I'm drawing crests. And they're supposed to be evenly spaced. Right? And off it goes. And you've probably seen this exact pattern. Waves in the ocean hitting a rock or going past a rock and doing funny things. So the rays that we talked about in the very beginning of the optics section, the rays are basically just perpendicular travel lines along these things, right? So a ray certainly could be this first one going straight like that, but notice I've got wavefronts all around this. So I've got rays which are going like this, like this, like this, and then as well as this way, and this way, etc., right? So the idea is that the narrower and narrower the slit, the more you try to make the light confined to just a small line, you're trying to collimate it, the less it works. Okay? Nature is rather contrary sometimes. So the more you try to narrow and narrow and narrow and get the light to be only a beam, the more it's going to start spreading out. And you may have noticed something like this if you've ever had a flashlight. Okay, you have a flashlight with maybe a circular lens, circular mirror behind the bulb, right? So that it would make a beam that goes out. But by the time the beam gets over there, it's way bigger, right? That's kind of the same idea. It's spreading out. All right, so we'll go forward from this. Like I said, this is a great model to have in your mind to help visualize things. But in terms of drawing things and getting qualitative things out of it, it's harder for me to use this one. I like drawing the actual sinusoids. So I'm actually going to erase this and go back to just the single slit. Okay, now, most of the light does actually go straight through the slit. Most of it. But we do get patterns going up and out here. Now, I would say that you've seen this before, but you probably haven't, because we haven't been able to do a two-slit experiment. But if you go and look at two-slit patterns, if you look at images of two-slit patterns, you'll notice that there's a bright set of interference fringes, and then they kind of darken off. And it's that darkening off that's due to this effect. What we notice about the intensity of the pattern on the screen here is that it looks kind of like this. I'm trying to make those secondary ones about the same size. So the diffraction pattern is that this is a bright fringe. And the bright central fringe is between here and here, because that's where the first dark one is. Okay? So our first diffraction minimum occurs here. And the same true down here. I'm just not going to write it. Now, in the sense that we were able to, in interference, chart the locations of minima, the dark spots, and the maxima, the bright spots, here in diffraction, we are going to find out where the minima are, and then we're just going to assume the maxima are halfway between. The reason for that is because the calculation of that is just a little bit more than we need to spend time on, okay? And I don't consider that a necessary part of this class. So, let's look at the first diffraction minimum. Where does it occur? Let's find the conditions and the positions of these things of the diffractive minima. Okay. Now, in order to do that, we have to play a couple of games. And so I'm going to go back to originally, you might ask yourself, what is different here about diffraction? Why are we calling this diffraction when we've talked about interference already? Well, there is no real difference. Sorry. Diffraction is basically interference. It's nothing different. It's all the exact same principles. It's the exact same wave thinking. But the difference is in the number of waves that you're considering. Now, when we were thinking about the double slit experiment, we were looking at, one wave coming out of one slit and one wave coming out of the second slit. Now, I'm going to have one slit. If I look at only one wave, I don't learn anything. There's no interference that I can derive from this because I need a second wave to interfere. The problem now is I'm looking at an infinity of waves, and this is also going on, by the way, in the double slit. It's just that when we did the double slit, we considered the size of the slits to be really small so that only one wave was getting out and we could look at that one, right? In order to let anything happen here, I have to have a finite size slit, and therefore an infinity of waves is coming through here. With that being said, I need to figure out what the condition of minimum of the dark spot is. What's the condition for this dark spot? Well, it's no different than it was for the double slit, right? I need to have two waves hitting each other out of phase, right? And they gotta be going like this, and they hit right there, and they cancel each other out. Okay. So let's look at that. But in order to do that, I have to think about how big the slit is and how the waves are going through the slit. Okay. So let's take one from here, like that. One from here, like that. Okay. Well, that didn't quite work out as I'd hoped, but nonetheless, reasonable. Okay, and one right here, like that. So I always get that last little bit of curving up right there. Okay, so what I've done is I've divided the slit into halves, okay? And I've drawn a wave, or a beam so far, but I'm going to draw a wave coming off the top half of the slit, a wave coming off the very bottom of the slit, and then a wave coming off in the middle of the slit, okay? Now, I'm going to divide this, and as Cantor would point out, I have an infinity of rays coming out, and if I divide the slit in two, I still have an infinity of rays coming out in half the slit. Is that infinity the same as the other infinity slit? I want to look at the waves here that are produced, not the waves that are produced, I want to look at the interference that's produced by the path length difference between these rays, between these waves. Okay, I'll get it right one of these days. Right, so out they come, they're all coming through like this, and I'm assuming they're all collimated and that they're all coherent. So they're starting at the same place in their wave travel, and I'm just going to assume looks like a basic sine. In order to get a better look at this, I'm going to redraw it bigger over here. Okay, so here's the slit, and I'm going to look at the wave that comes out from the top here and the wave that comes out from the middle. Okay. I was fortunate enough to be able to basically draw these about right. Okay, so the path length difference, just as we did with the double slit, right? I'm going to drop this perpendicular here. Everything after that, they're all traveling the same number of wavelengths. Therefore, the path length difference And how many wavelengths fit in here completely determine the diffraction slash interference that I'm going to get on the screen. I'm going to employ the exact same techniques as I did before. The angle coming off here, theta. Now notice I am at halfway down the slit, so really now the path length difference isn't d sine theta or anything like that. It's half of the width of the slit. Okay, so what I'm going to do is I'm going to call the slit width A. The total slit width from here to here is A. And therefore, this part here is half A. Okay, the path length difference then is 1/2 A sine theta. Same exact argument as before with the double slit where I had d sine theta. It's just that instead of d, I've got 1/2 of A, and A is the entire slit width. Okay, now, to get to the first minimum, I have to have half a wavelength in my path length difference. So, 1/2 A sine theta should equal 1/2 lambda. That gives me my first diffractive minimum. And that leads us to the wonderful condition that A sine theta is equal to lambda. And that's what happens to determine angularly where the first diffractive minimum occurs. All right? Now, what about the other half of the slit? What's going on down here? Well, if a wave at the top and a wave in the middle are half a wavelength out of phase, then wouldn't it stand to reason that a wave in the middle and a wave at the bottom are also a half a wavelength out of phase? Yeah, it would. So, I can do the exact same thing, draw the exact same path length difference, and find out that I'm going to have a half wavelength here. Like so. And you're going to say, well, wait a minute, now doesn't that reinforce with this one? Well, no, because that one's been canceled by this one. And you'd say, well, wait a minute, what happens to this one? Well, how is this one getting canceled then? What we're doing is we're thinking about pairwise cancellation. Remember I told you there's an infinity of waves here, okay? There's an infinity of waves, so that if I look at the one that's right at the very top and the one that's just right here at the middle, there's a half wavelength between those. So if I go a little bit further and a little bit further and a little bit further and a little bit further, all these waves are pairwise canceling, okay? The one in the middle has a wave right next to it that has the exact same phase and will cancel with this one, right? That's why we get a dark spot, because the waves are all canceling. So the way I've drawn it possibly makes you think, well, wait, there's one wave left over. There isn't, because there's an infinity of these things, not three. Okay? This leads to pairwise cancellation. Okay? So it's as if I'm doing a limiting procedure on something that is continuous. Okay? But we have to recognize it's continuous. I can take and say, look, I can go a small little bit down here and look at the wave that's right next to this one and right next to that one and right next to that one and right next to that one, and I will find all those phases are exactly a half wavelength out of phase with all the ones right down here, which I went down the same exact amount, down the same exact amount, down the same exact amount. But we're chopping this up, and we have to chop it up finer and finer and finer and finer. It's just going to become continuous. There are an infinity of waves coming through here. They cancel each other. don't try to overthink it in the sense that, wait, when I draw it, I've got this extra wave left over. It's not happening in only small bits of waves, right? It's happening with a huge number of waves, more than we can possibly keep track of, and this is just representative of what's going on. All right, so if I wanted to then say, what about the second diffractive minimum? What about the one up here? Here's the first diffractive minimum, the second one's occurring over here. How would I do that? Well, I could employ the exact same technique. I just got to slice up the slit into, say, quarters, right? And say, well, I'm going to have this one canceling with this one, canceling with this one, canceling with this one, right? And then I would find out that the exact same condition would hold, but with a 2 lambda difference now, right? So ultimately, the entire minimum set is determined by this thing with an integer number counting in front of the wavelength, just like we did with the double slit. So what we find here is that the diffractive minima, actually I guess I do have to. So to find all minima, they're going to be located at m lambda. Where the integers are not starting at 0 this time. Okay? And remember, this is for minima. In the double slit interference, we had an expression like that with a d that was for the bright fringes, for the maximum. So just remember that when we get to diffraction, it changes a little bit, okay? So the diffractive minima are located at these angles, sine theta, right? You swing the a underneath and you have a lambda over a, and you say it's number 1, number 2, number 3, blah, 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 okay? Now, that's where the minima are. Like I said, we don't have the time involved to go through and look at how to find where the maxima are. Nonetheless, what we can do is things that are fairly straightforward, like I can find between where and where each maximum is. Because I can find the minima, I can tell you where the maximum is between. So, for example, take an easy case like the central max. The central maximum occurs between these 2 minima. If I find these 2 minima, then that's where the central maximum is. And likewise, I could go down to this one. I can find this minimum, I can find that minimum. I can say, well, the number 1 bright fringe is between these 2. Okay? The easiest thing, which is mostly, it's good enough, it's a good rule of thumb, the bright fringes are just halfway between, kind of like they were with the interference effects. Right? They were evenly spaced. So just consider that between the 2 minima lies a maximum, and we can just assume it's about halfway. Therefore, the width of the central bright fringe, we can find that width. Okay? We can find that width, maybe it's called W. Width, and I'm going to say that's equal to 2y1, because y1 would be from the center point up to the first diffractive minima. Okay. Just like we did with double slit, we can assume a small angle situation here, such that the sine and the tangent are approximately the same. Sine and tangent are about equal. So if I do that, then I can go into this and kind of run the same game. All right. That means I can take this and use a times y1 over d equal to lambda. And and therefore I get a y1, which is, what is it? It's capital D divided by A. Okay, so that would be y1, and this width of the central maximum would then be twice that. And we'd be able to find how large the maxima are by looking at the positions of the minima and doing a difference or an adding or whatever is necessary. All right. Okay. Good times. So why don't we take this now and take a look at finding some, oh, you know what we can do? Let's do this. We can find a wavelength here. Wavy. Okay, so got a little example here where we have light going through a slit. Okay, and the slit width we know. Let's suppose that it casts a central maximum on a screen which is about a meter away. Let's say that this is about 0.85 of a millimeter. That's pretty small. On a screen 1 meter away. What's the wavelength of the light that we're dealing with? Okay. Real easy way to determine the wavelengths of things. Cast them through a single slit, cast them through a double slit, and look at the pattern and then measure what's going on with the pattern, and you can figure out what the wavelength is. So in this case, I know that the width, this is the width of the central maximum, is that. So if I just rearrange to find wavelength, then I'm going to multiply the A and divide by the 2D, like so. And we're going to multiply 0.85 times 0.12 over 2 times. Now, these are in millimeters, so what's going to happen is this wavelength's going to come out in millimeters. So if I do 1,000 here, put it all into millimeters, I'm getting a wavelength that's coming out in millimeters. And this is pretty small for millimeters. But if you then convert it into, nanometers, it's going to turn into 510. Right? So, going from nanometers and millimeters and meters, if you are not pretty well fluent in doing that, you might want to just refresh yourself on what the metric prefixes mean, right? 3, 6, 9s, etc., like that. So there's 10 to the 6th nanometers in a millimeter, so you can have that factor in here as well. All right. Good. So one question about this is, I did assume over here that the angle was small. Is that valid? in this situation. Why don't we check the angle just to make sure that it is a small enough angle such that I could do something like this analysis and bring it over here, all right? So let's check the angle to the first diffractive minimum. So this would be sine theta being lambda over A. Now, if this is true, then I would say that, right, my sine and tangent are almost the same, and in radians, those would be equal to the angle by itself. So if we calculate lambda over A here, lambda we know is 510 nanometers. If we take the slit width here and we put it into nanometers, that's 0.12 million. So what does that mean? 0.12 million is 120,000. So does that seem like a small enough angle? So this is something around. Just get rid of these two, get rid of those. 5 and 12. It's like 1 and 2. This is about 1. Well, 5's not really 2, so it's more like, yeah, it's not that bad though. It's like 1 in 2,000. So it's a pretty small angle. I would say that it's reasonable, even if you get to, and you can check this, I think I've said this before, but you can check this to see how well that small angle approximation does, even when you get up to something like 30 degrees, right? 30 degrees is pi over 6, and pi is 3.14 divided by 6, so you're close to a half right there, and that's a 30-degree angle, okay? Where you're talking about a 0.5 radians. This is nowhere near 0.5 radians, so I think we're safe. Nonetheless, this is typical for a small angle in a single slit and even in a double slit experiment also. The angles are so tiny because of the slit spacing and the slit sizing compared to the wavelengths. All right. Okay, so we have this. Let's talk about intensities now that we've kind of dealt with diffraction minima and where they are angularly and where they are located on a screen. Let's talk about the intensity pattern of the single slit. Now, the single slit is a lot different than the double slit in the sense that the double slit was a situation in which there really wasn't any decreasing in the intensity. Okay? It just depended on what was the relative angle of the electric field vectors. All right. Well, we can do the same thing here with a slightly different twist to it. All right. So, drawing a rather large slit here. Now I talked about the infinity of waves that are coming through. So when you think about waves, this is a little bit of a new model, but it would be really useful in a little while. When you think about a wave traveling, one of the things that physics has come up with is a picture of how to think about this in your mind, and basically it's like a clock, or maybe if you think of like a surveying wheel that you're rolling along the ground, okay? You can think of it as a little arrow that rotates. So as the wave starts off, maybe, let's see, what would we do? Let's say that we start off at 0, so we're pointing this way. And by the time it gets up to here, now it's rotated like this. Well, maybe I should rotate clockwise. All right, so maybe I'm going to rotate it's going to come back up. And by the time you get back up here, it's turned. And by the time the wave gets down here, it's turned again. Right? So you're thinking of like if I had a right? If I had a unit circle, right, or a surveyor's wheel, or something like that, right? So as we roll this forward, right, it rolls like this, and then so the next thing I'm going to see is the vector pointed like this, and then the next thing I'm going to see is the thing pointed like this, and it's going around, right? But ultimately, that's how we connect the sinusoids of trigonometry with the geometry of triangles, right, is by this unit circle. So if I just pop on here, if I pop in here a set of axes, then you'd recognize, if it goes counterclockwise, that's easier. Right, if it goes around like this, you'd recognize this. Oh, there's a little delta theta here, and it's going around at an angle, and it's going around at an omega, which is a frequency. Okay, so let me get rid of this so it's not way here. I shouldn't have walked that way. I guess I should have walked this way. Oh, that's what I'll remember that for next time. I should walk that way so I can get the wheel traveling counterclockwise. The position of this bead on the circle, the position of this point on the circle is given by the sine and the cosine, right? So here, the y position is 0, the x position is maximum, and that just corresponds to x being, for example, r times cosine theta, and y being r times sine theta. And here, where theta is 0, then I have the cosine, and I have 0 in the sine, and by the time it gets up here, they're like halfway, and then by the time it gets up here, there's 0 in the x, and it's all in the y, and my angle is 90 degrees. So thinking of this little arrow moving around as a wave travels, right, is a really useful thing to think about. So it's almost as if you're thinking of, right, I try to superimpose the wave here, but I don't know how to do that. So you just think of the thing going around, well, it's going like this. Well, see, that's the thing. Now, I want it to go this way as the wave goes this way, but it looks weird if I do that. So if it's up here, it's up like that, and it's kind of, and it's going down, and then it's going down, and now it's back to here, and now it's back to there, etc., etc. Okay. So you can imagine that coming out of this slit are an infinity of waves who we can represent as just simple arrows, right? So if I got all these little arrows like this, maybe they're all ready to go. They're all pointing that way, okay? This is the hallmark of coherent light. They are all starting at the exact same place in their wave, okay? Now, as I shine the light through the slit and I try to catch them on a screen that's way over there, I guess by scale it would have to be a mile that way, but nonetheless we'll draw the screen like here. Okay? These things are all going to hit the screen and they're going to make a bright spot where they constructively interfere with each other, right? So if I consider, for example, the slit being small, I'm going to consider this spot on the screen and I'm going to say, well, what light is hitting these things? How do their arrows line up? Right? So ultimately, what effectively is the total electric field at that spot? So I might say, well, here it's going to be this, plus this, plus this, plus this, plus this, plus this, plus this. Okay? So my total electric field vector is going to be this whole entire thing. Right? Call this, for example, E total. Whereas it's a sum of all these individual little electric fields of every little electromagnetic wave that's propagating from the slit and hitting the screen. You'd say, okay, that's great, but what happens? Well, let me back up for a minute. Why are they all still in a line like this? Well, they're in a line because they all rotated the same exact amount, and by the time they hit here, they were all lined up again this way, right? Now, what if we go to a spot way up there? Now, you know I'm going to have a path length difference because the ones on the top are not going to rotate because they only had to do that many, whereas the ones down here had to do that in order to get up there, right? So now I've got a path length difference between all of these waves as they hit at a spot up there. Well, if they hit all such that they are going, right, so let's do this up here at the first diffractive minimum. Let's get this out of the way. Here we are at the first minimum up here. Oops, minimum. Right, at the first minimum, then what's happened is one of them is still kind of lining up like this, and then the next one had to have gone a little further, so it's like this, and then the next one's a little further than that, and then the next one's a little further than that, and the next one's a little further than that, and it's further than that, and it's further than that, and it's further than that, and there they are. Now they're all lined up, right? But I have added these vectors all together. And what have I gotten? Can you see I get 0 if I add all these vectors together? That means the electric field I'm expecting at that point, due to the electric fields of all the individual waves that had a path length difference now, is 0 here, and I'm expecting a dark spot here. And this is where E equals 0 because they all join up perfectly. I get 0 resultant electric field at that point, okay? So what we can start thinking about then is what happens if I'm at a point in between here? Can I find out something about the intensity, because it's not fully constructive like it is here, and it's not fully destructive as it is here? Can I look inside the central maximum and determine approximately what's the intensity inside the central maximum when I'm slightly off the exact central max here? All right. So it looks like that's about what we might be picking up with starting tomorrow. Okay, remember that homework is due tomorrow and quiz tomorrow. So I'll have the quiz posted up and I will try to get that ready to go so that you can take it at your heart's content, although most of you seem to take it in the afternoon, but that's okay. Don't forget PLC 9 for this Friday is all on interference, okay? When homework 5 is done, we're going to have homework 6, which is going to be on diffraction and will be due the day of the second celebration, and that will hopefully, we might have a few things to tie up after that, but nonetheless, that should be just about the end of our diffraction journey. Okay, so we are rolling. This is the middle of the week past spring break, so good luck to you all. Have a great rest of your day, and I will talk to you tomorrow or whatever.